Okay guys, so today we're going to talk about the relationship between three things that we've been studying around circuits: potential difference, current, and resistance. So before we get on to kind of getting a mathematical relationship between these three variables, let's just review over the symbol that we use for these three things, the unit of measurement, and their definition. So can I get somebody come up to the board and have put the symbols up? Yeah. Good. So we use V for potential difference. Right. I for current, to represent current. And R for resistance. Perfect. Good job, Janet. Okay, can I get somebody else to come up and put the unit of measurement? Yeah, is that you? Perfect. Volts. So potential difference equals something we call voltage, and we use volts as the unit of measurement. Current is amperes. And resistance we measure in ohms, and we use the symbol omega, because the Greek letter omega. Okay, and get a last person to come up and have the definitions. Jeez. Good. So, for those who can't see, potential difference is the difference in electrical potential energy per unit of charge. Right? Okay. Current is the rate at which electrons flow past a specific point in the circuit. And resistance is the opposition to the movement of electrons as they flow through the circuit. Okay, perfect job, guys. So before we move on, let's just go over a few of the things, factors that affect resistance of the circuit. So we have material, length, temperature, and cross-sectional area. So resistance, I want you to kind of think of electrons flowing through a circuit. Think of this analogous to kicking a soccer ball on a field, right? The longer the grass, the harder it is for the ball to roll across the field. The harder it is for electrons to move through a circuit, right? So the type of material, right, if the wires are conductive, or their conductivity will determine how much resistance the electrons incur as they go through the circuit. The length of the wire also matters. The longer your wire is, the more the electrons have to travel, and therefore the resistance is increased. So we say that length is proportional to resistance. Another factor that's important is temperature. As the temperature increases, molecules move faster, right? We remember that from our chemistry. And also, as the temperature increases, the electrons are moving faster, and so there's also an increased resistance there as well. And the final aspect is cross-sectional area. So basically, how wide our wire, or how big our wire is. The larger the wire is, the less resistance there is. There's more room for the electrons to flow, they can flow easily. The more compact your wire is, the electrons are all smushed together and the resistance is higher. So basically, cross-sectional area is inversely proportional. As one increases, the other decreases. Okay, so now that we've got those all down pat, we're going to talk about somebody called George Ohm. Okay, so he's the one that kind of first made this connection between potential difference, current, and resistance. So just how we've been playing with circuits in class, he also had free time, and he would play around with these circuits. And what he would do is modify, he would keep certain aspects of the circuit constant and modify other aspects. So what he noted was that when he set up a circuit and he would measure the voltage, he also saw there was a concurrent increase in current. So as voltage increased, current increased. Which probably is 5. That's the symbol reading, okay? Current increased. Okay. And another thing that he did was he changed the length of the wire. So going back to what we did with the wire, if we change the length, what would happen to the resistance?
It would increase so it's longer?
Right, it would increase. So when he changed wire length, he found that resistance increased. When he measured the voltage in the circuit, he noticed, however, that the current decreased. Right? So based on these observations, he was able to come up with a formula which he calls Ohm's law, which is V equals I times R. Potential difference is equal to the product of the current and the resistance in the circuit. And we can rearrange this formula to solve for either one of these variables. So if we wanted to solve for current, what would we do to this formula?
Divide by R.
Divide both sides by R, right? If we divide both sides by R, we get a new formula. Current is equal to voltage over resistance. And if we want to solve for resistance, what would we do to our main formula? Divide both sides by I, right? We divide both sides by I, we get a new formula. Voltage, resistance is equal to voltage over current. Okay, so let's run through some number examples. So I've got, shall we leave our formula on the board? Okay, so I've got a circuit here. And let's assume for this circuit that we know that the battery has a voltage and we know the current in the circuit. So yeah, let's say it's a 9-volt battery and the current is 2 amperes, right? What would the resistance of this load be? Which formula are we going to use?
V divided by I.
Right. So if we rearrange this formula, V divided by I, and so we get 9 volts divided by 2 amps would be
4.5.
4.5. Right. 4.5. And what would the units be?
Ohms.
Volts. Okay, good. This is what I remember. Okay, let's do another example. This time we have, let's change it up and let's have a 12-volt battery. And this time we are given the resistance of our load. We know that the resistance is 3 ohms. What's our current going to be? What formula are we going to use and how are we going to determine the current?
V over R.
Right. I is equal to V over R, potential difference over resistance. So our voltage is 12 volts. Our resistance is 3 ohms. And so our current is going to be?
4.
4 what? What are the units for current? Amperes. Perfect. Okay. One last example. Can anybody guess what we're going to solve for this time? Right, voltage. Okay, so let's say we're doing resistance. Our resistor is 2 ohms. Our current is 3 amperes. How are we going to calculate voltage?
3
Right.
times.
I times R.
I times R.
2.
So 3 amps times 2 ohms. That would be
6 volts.
6 volts. Okay, good job, class. So actually, let me just put the answers for all 3 questions that we did on the board, and we're just going to quickly compare. So in our first example, we had voltage of 9 volts, current 2 amperes, and we calculated that the resistance was 4.5 ohms. In our second example, we had a voltage of 12, a resistance of 3 ohms, and a current of 4 amperes. And in our last example, we had current of 3 amps, a resistance of 2 ohms, and a voltage of 6 volts. So I put these numbers up again just to kind of reassure what the answers that we get make sense with Ohm's law, right? As we discussed earlier, what Ohm discovered was that current and resistance are inversely proportional. As you increase one, the other decreases. So looking from the first example to the second example, as the current went from 2 amperes to 4 amperes in the circuit, we also see a decrease in the resistance, right? So there's an inverse relationship. Similarly, from Ohm's law, we know that voltage and current are proportional. So if one increases, the other should also increase. We can also see that, and from example 1 to example 2, when we have a battery that has an increased voltage, we also see an increased current. So, and basically the main point of this lesson, Ohm's law can be used to describe the relationship of potential difference, current, and resistance in a circuit.